Hello, everybody. It's time to continue our discussion about the sun. And this time, we're going to study the interior of the sun. We're going to start at the core and go all the way to the visible surface of the sun, the so-called photosphere. And we'll look at how energy is created and transported to the surface. So this is really going to be a story of how a photon created by nuclear reactions in the core of the sun by fusing hydrogen into helium will make its way to the surface of the sun where it can escape to space, travel throughout the solar system, come into Earth's atmosphere, fall down to the surface of the Earth, and fall into your eye as you sit outside on a nice fall day, a sunny fall day, and look up at the sky. All right, so let's follow our journey of the photon through the sun. But the way I'd like to start this video is because I know it was somewhat of a tricky concept. I want to remind us all of how we actually know the interior structure of the sun, which was this field of science, this branch of astronomy called helioseismology. So the sun is producing energy in its core through nuclear fusion, and then it has to move all of that energy to the surface, which means that there are a lot of internal pressures. You got gravity that's crunching the star together, and it's equally balanced out by the thermal pressures pushing outward. The sun is in a hydrostatic equilibrium, but there are still a lot of internal roilings about, which send out sound waves, a type of pressure wave throughout the sun, which the sun being a nice spherical object, all of these vibrations and oscillations settle into a nice pattern in the sun of a whole lot of different frequencies, a whole lot of different vibrations. The sun is ringing like a bell. Well, how those waves are traveling through the sun, which are depicted here in this wonderful graphic, how the waves are traveling through the sun, the path that they take, is determined by the interior density structure of the sun. So if we can study the pattern that the waves make, we are really studying, the pattern is determined by the density structure of the sun. So we are really studying the interior density structure of the sun. Sure, there's a lot of fancy work and a lot of cool mathematics and physics that goes into actually looking at the pattern of these density waves, how the sun is ringing like a bell, and turning that into the interior density structure. But we can do that. And that field of study is called helioseismology. And it gives us the interior density structure of the sun so that we know the interior layers of the sun and how deep they extend to, how big they are in the interior of the sun. But over this video and the next video, we will cover all the layers of the sun. So this video, we're going to go with the internal layers, the core, the radiative zone, and the convective zone. And we will end at the surface of the sun, the photosphere. We'll save the chromosphere for the atmosphere of the sun. So let's go ahead and get started. And let's just take a look at a cross section, a cut into the sun, so we can see all of the interior layers that we want to know more about. So this video is going to cover the interior layers, the core, the radiative zone, the convective zone, and the visible surface, the photosphere of the sun. The next video is going to be about the atmospheric layers. So here we have a picture of the sun. We have both the visible surface, the photosphere, which then we have the first atmospheric layer called the chromosphere. That's what you're seeing here. But what we're looking at here is this cut out of the sun. So we want to take a look into the interior of the sun. Of course, this is just a graphic produced by NASA, but the very center of the sun, we have the core. Just outside the core, we have a region of the sun called the radiative zone. Above the radiative zone, we have a section called the convection zone. And then sitting just on top of the convection zone, a very thin layer called the photosphere. And whenever it comes to actually naming the layers of the sun, astronomers are wonderfully creative. And we call the center of the star the core. Great job, nailed it. And then we call the radiative zone because the energy is transported via radiation. Again, just doing a wonderful job with our naming here. The convective zone, the energy is transported up towards the surface of the sun by convection. Like if you heat up water and then you can see the water moving around, setting up convection cells. So we're very, very on the nose with naming. And the photosphere, photo, same root word as photon, meaning light, sphere, meaning sphere, realm. So this really means the sphere of light. Kind of a cooler name, but still very on the nose. Okay, so let's go through each layer and talk about how energy is created and then transported to the surface. So the core of the sun, the very central regions of the sun. And the way we're going to talk about this is we're going to go from the center outward. So we would say that the core goes from the center of the sun to about 25% of the way to the surface, from about 0 to about 0.25 solar radii. And what defines the sun or the core of the sun? Anywhere where you have nuclear fusion happening, where you have hydrogen being forced into other hydrogen atoms and then becoming helium, where you are literally fusing hydrogen atoms together to become a different element, helium. So anywhere where nuclear fusion is occurring, that defines the region of the core. So nuclear fusion happens all the way in the central parts of the core, all the way to the outer edge of the core. And what is nuclear fusion? When I'm just going to start saying fusion. So what is fusion? It's the combination of two lighter elements into a heavier atomic nucleus. So you'll take two light atomic nuclei, like hydrogen, or you'll take hydrogen nuclei and fuse them together. And through a series of reactions, you can fuse things together until you end up with a helium nucleus. And that's what's powering the sun. So energy is produced by fusion in the core of the sun. And the fusion reaction is fusing hydrogen, element number 1, into element number 2, helium. And in this process, you produce a boatload of energy in the form of gamma rays, light. The core has an extremely high temperature. And yes, we are going to care about the core temperatures of stars because that tells us what kind of fusion is happening in the core and whether or not fusion can occur. It also tells us how fast fusion is happening, how fast we're fusing hydrogen to helium, how much energy we're producing is all determined by the core temperature. And the temperature of the sun the core temperature of the sun is 15.7 million Kelvin. That's a huge temperature, 15.7 million Kelvin. If you're curious, I won't talk about the density of the other layers too much. I'll mention it here or there. You don't have to memorize the densities of these layers, but the density of the core of the sun is about 16,000 or 160,000 kilograms per cubic meter. So if I were to draw a box that's about a meter by a meter, and then a meter in depth, and I had a cube that's a meter by a meter by a meter, a cubic meter, and I put solar core material in there, that cube would weigh or would have a mass of 160,000 kilograms, which with such a high density, even though it only goes 25% of the way to the surface, the core contains 34% of the total mass of the sun, even though it's only accounting for 0.8% of the total volume. The core is the densest region. As you go deeper, things get pushed together, gravity pulls things together tighter, and the density is higher, which also makes the temperature higher. And maybe I can relate that a little bit better. If I had a 12-ounce soda can, man, I wish I had a soda can with me. If I had a 12-ounce soda can of solar core material, and we had it here on Earth, in Earth's gravitational field, it would weigh about 125 pounds. Okay, so energy is produced in the core by the fusion of hydrogen into helium. And then what happens to all of that energy? The energy is that's being produced in the core through all those fusion reactions is light. Comes out in the form of gamma ray light, the shortest wavelength version of light, super high energy light. And what it's going to do is outside of the core, the way that we transport energy, the way that we move energy from one place to another, where we're going to take the light that's from the core and move it, where we're going to take the heat that's produced in the core and move it towards the surface. So it's really about how we're transferring the heat energy here. And the heat energy is going to be transported by light. You might be sounding, that sounds weird, heat transferred by light. Go turn on your stove or stand right next to a fire. You can feel the warmth of the fire, right? What are you feeling? You're feeling the bombardment of infrared radiation going into your body, making you feel all nice and toasty. So yes, you can transport heat energy by light. That's black body thermal radiation. So in the radiative zone, we're going to be transferring the energy towards the surface by radiation, giving it the name the radiative zone. Man, we are so creative here. So, how can you remember what the radiation zone is? It's the one that's above the core, and light is transferred, or energy is transported by radiation, light. However, it's not a simple path for those photons created in the core to make their way through the radiative zone on their journey towards the surface, where they can eventually go into outer space and we can see the sunlight. So, produced in the core by fusion, or energy is produced in the core by fusion, then it travels through the radiative zone as light. But with the extreme temperatures and densities that the radiative zone has, I didn't mention the temperatures and densities are still in the millions of Kelvin. The densities are still crazy, crazy high. The high temperature means that you're not dealing with atoms in the radiative zone, you're dealing with ions. The high temperature strips away all the electrons from the atoms. So you have a bunch of ions, charged atomic nuclei with some number of electrons or no electrons, and then a bunch of electrons running around with pretty much no electrons to absorb light to move them around in the various energy levels. What ends up happening is, since we have all these ions and the density is really high, they're all packed really close together, that light is going to be traveling through a kind of a thick soup of plasma. Remember, plasma is just a gas made out of ions and electrons. The atoms that have their electrons removed and the electrons that have been removed. So what happens to this? Let's imagine a gamma ray particle trying to make, or gamma ray photon trying to make its way through the radiative zone. That's going to be a really long and hard path for this poor lonely gamma ray, because it's traveling through such a dense soup of ions and electrons. And since everything's packed very close together, you'll say produce the gamma ray in the core. So it's produced by the fusion reaction, and it doesn't make it very far, only a few centimeters on average, before it's going to run into an ion or an electron. And it's going to bounce off that ion or electron, and it'll go off in a random direction, a so-called scatter. And within that reaction, whenever the photon comes and here's an ion, the photon boop, bounces off of it. Some of its energy is going to go into the ion or the electron that it hit. So now our photon will have lower energy, which means it'll have a longer wavelength. And every few centimeters, it's going to bounce into another one. So it's going to travel, hit something, go off in a random direction, scatter, 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 and what's called a random walk, or sometimes called a drunkard's walk. And each time it bounces off an ion or electron, it's going to lose a little bit of energy, shifting it from the gamma ray portion of the electromagnetic spectrum to shorter, or to longer and longer and longer wavelengths, through the X-rays, through the UV, and eventually down towards the visible part of the electromagnetic spectrum. And this path, this random walk, yes, it'll slowly make its way statistically away from where it was produced, away from the core, but it's going to take a long bouncy path to get there. And so-called Brownian motion, also called a random walk or a drunkard's walk. So how long does it take? Let's say we have a gamma ray produced in the core, and it scatters over and over and over again out of the core into the radiative zone, all the way to the top of the radiative zone, losing energy with each one of those scatters. It takes it about 150,000 years to go through the radiative zone. That is crazy. It takes 150,000 years for that photon to scatter its way out of the radiative zone. But what happens at the top of the radiative zone? Why is there a transition from a radiative zone to the convective zone, the zone that sits right above the radiative zone? So eventually it will bounce its way all the way up. But what's happening is the density of the sun is becoming less and less and less, and the temperatures are getting smaller and smaller and smaller. And as the temperatures get smaller and smaller and smaller, and the densities are less, things are bouncing off each other, the thermal motions are lower. And eventually, those electrons can actually get rebound to the atoms. You're not dealing with ions anymore. You get electrons that are bound to the atoms. It might still be slightly ionized, but you now have electrons on the atoms, which means if you have an electron that you can move through energy levels, all of a sudden that photon that bounced its way all the way through the radiative zone, once it hits something in the convective zone, it can interact with that electron and make those electron transitions. It can get absorbed all of a sudden. We would say that the gas, as it enters the convective zone, is now opaque, where all of a sudden, all the light that's coming out of the radiative zone will get absorbed by the atoms and the ions in the convective zone, which means that it's going to dump all of the light's energy into the actual atoms, into the substance of the sun, into the material that makes up the convective zone, which you can imagine that's going to be like you're cooking it from the bottom. And whenever you have something that's hot on the bottom, and then it gets less dense and cooler as you go up, then that is the correct situation to set up a form of energy transportation. Go see the notes for details, called convection. You can think of boiling water, where as it heats up, it becomes less dense and will float up, it will rise up. And then as it rises higher, it'll cool down, which will cause it to become more dense, and then it'll sink, where it gets heated up, and then it'll rise and then sink, setting up these nice convective cells of hot material rising, cooler material sinking, hot material rising, cooling material sinking. So now we're not transporting our heat energy via radiation, we're transporting our heat energy via convection, and we're in the convective zone. And where is the convective zone? So the core went out to 25% of the radius of the sun. The radiative zone went from 25% to 70% to the surface of the sun. And the convective zone will go from 70%, 0.7 solar radii, all the way up to the very surface of the sun. And this is a layer, so this is the layer that's just beneath the surface of the sun. So it's sandwiched between the photosphere and the radiative zone. And energy is transported via convection, and it's setting up these nice convective cells. But it's not as simple as you don't just set up one, it doesn't just all rise all the way up from the top or the bottom or the top of the radiative zone. It doesn't rise all the way up to the surface. The way that it will naturally set up, the way that physics will work, is it'll set up convective zones on top of convective zone, or convection cells on top of convection cells on top of convection cells on top of convection cells. Each time, each convective cell getting a little bit smaller, so it'll transfer some material up, and then there'll be a zone on top of that, and a zone on top of that, and a zone on top of that. So you have all of these convective cells here in the convective zone or convection zone, that's slowly moving that material, that heat energy, to the surface of the sun, where eventually it'll reach the surface of the sun. So now we have finally reached the surface of the sun. We can now have the light, the thermal light of the sun, the black body radiation of the sun, that has a black body spectrum set at the temperature of the surface of the sun, can freely escape to outer space. Let's talk about how that happens. Let's continue our journey of how that photon that you created in the core will eventually make its way into outer space so it can come to us here at Earth. And remember that as we move away from the core, the densities are getting lower and lower and lower and lower. Eventually, whenever it reaches the top of the convective zone, the densities are extremely low, about 2 times 10 to the minus 4 kilograms per cubic meter. So if I had a box that's a meter by a meter, a cubic meter, all the material, the solar material in that box at the surface of the sun would only be 2 times 10 to the negative 4th kilograms worth of material. That's 6,000 times less dense than air. So very, very thin. And with so little material there, there's just not enough atoms to absorb all of the light, the thermal blackbody light being produced by the solar material. the hydrogen and helium of the sun. That's really, really, it's dense by standards to produce a black body in this case. But there's just not in this region right here where we get to the photosphere, the densities are dropping super fast. And there are just not enough atoms. So the black body that has the surface temperature or that radiates at the surface temperature of the sun, all the light that's there, it can freely just go through all the layers above it. There's just not enough atoms there for that light to have a good chance of running into one and getting absorbed by that atom. So light is now free to escape to space. We say that at the photosphere, this surface of the zone, of the sun, the top of the convective zone, that the gas has become transparent to visible light. So visible light photons can escape the sun. Now, our visible photons are free to go out into the solar system and eventually come into Earth's atmosphere, and warm us up. This transition from a opaque to a transparent region where the light can freely escape happens in a very, very short distance in the sun. So you reach the top of the convective zone, and then within 500 kilometers, remember that the sun is about 700,000 kilometers in diameter, but within 500 kilometers, a very thin layer compared to how big the sun is, the densities drop so rapidly that light can freely escape from this region of the sun. And it's only 500 kilometers thick. So it looks like a very well-defined surface to us because it's so thin where this happens. It looks like all the light is coming from the same region of the sun, giving us this visible surface of the sun, this visible sphere of the sun that we call the photosphere. So the photosphere of the sun is the visible surface of the sun. It's what we see. And you can see it looks like it's very well defined because where you can actually see the light coming from is a layer that's only 500 kilometers thick. So picture 500 kilometers on top of 6,900 or 696,000 kilometers down to the center, which gives us this nice thin layer that looks like a surface. It has a temperature of 5,800 Kelvin and is acting like a black body. Therefore, it gives off thermal radiation, a black body spectrum, with a temperature of 5,800 Kelvin. Also the photosphere, so here's an image of the photosphere. You can see that it has these blemishes that Galileo once noticed. This is it's on the photosphere that you see sunspots. So the sunspots live on the photosphere. And if you were to have a really, really, really high resolution, a highly detailed picture of the surface, so you could look at it really up close and still see all that detail, you'd notice that the surface of the sun has this sort of granular appearance. Looks like a bunch of little grains that are sort of patched together, where you have these dark centers and then these these bright centers and then these dark edges. We call this granulated surface of the sun the solar granulation, because again, we're good at naming things. So what creates this solar granulation? Well, remember that the photosphere is sitting right on top of the convective zone. So just below it, you have these convective cells where it's bringing up hot material and then cool material sinking at the edges. And if we can remember our stuff on Boltzmann's law, hot stuff gives off more light. So here we have the bright part where the hotter material is coming up the top of a convective cell. And then it goes around to the edges where the cool stuff is sinking back down, cooler, giving off less light. You have these darker boundaries. So we are literally seeing the tops of the convection cells on the photosphere. And yes, you can see that they change over time. This is an animation of the convective cells on the surface of the sun, these solar granules, as we call them, where the granules, the granules are bright because we're seeing the top of the convective cells where the hot material is coming up, and they're dark on the edges because that's where the cooler material is sinking. So we have this granulated surface. And here's a sort of cut away where you can see hot materials coming up. So then this material will be hotter. And since it's hotter, because of the Stefan Boltzmann's law, how bright something is, its luminosity, its brightness, how much energy it's giving off is proportional to the temperature of the fourth power. So it's going to give off more light, appear brighter. Check. And then at the edges, that's where the cool material is sinking back down. It's going to be cooler, so it's not giving off as much light, so it's not going to appear as bright, so it looks darker. And each one of these granules, the tops of these convective cells, are about the size of Texas. They're about 100 kilometers in diameter. So that's a Texas, that's a Texas, that's a Texas, that's a Texas. So they look really small on the surface of the sun, but the sun is huge. So each one of these is actually quite large by terrestrial standards, Earth-based standards. And what's even cooler is not only can we see the top of the convective cells, we can actually measure the convection itself because that hot material is coming up towards the surface of the sun. That means it'd be traveling toward the Earth. And where it's sinking back down, it's going back towards the center of the sun. It's moving away from the Earth. So we can actually see that the spectral lines from this region are blue shifted, moving towards the Earth, move to shorter wavelengths, and the ones at these edges are red shifted. So we can measure that Doppler shift, which gives us how fast the material is moving, which is about 0.4 kilometers per second, about 400 meters a second, which is pretty darn fast. All right, so now we know how our photon was created in the core of the sun by fusion, and over 100,000 years slowly made its way out of the core through the radiative zone by radiation, by light transfer, into the convective zone where convection carried the heat to the surface, where the sun became thin enough where the light could freely escape to outer space, and that gave us our photosphere. All right, you are an expert on the interior structure of the sun. Thank you for tuning in. Next we'll talk about the atmospheric layers.